Hi there, and welcome back to another online lesson in BCIT's Technology Teacher Education 5060 course. Today we're going to be talking about H Bridge motor control for our Tethered Mini Sumos. Now, we're going to use H Bridge motor control actually on a chip running with a circuit board to make our boom bots a little bit later on. But since we're starting out with a project for grade 9 and 10 type students, we're just going to build a manual H Bridge that you can hold in your hand, and we're going to talk a little bit about how it works today and how to go about making one. So grab a cup of coffee and kick back and enjoy. Now, for my students in technology teacher education, you should be able to find this presentation on D2L, our learning hub, at under the Mini Sumo tab, kind of down towards the bottom right in here. 5060 H Bridge motor control. That's the PowerPoint presentation. You can download it if you want access to the drawings and all that that we've got in here. So let me just bring this back now to our slideshow, and let me provide the exciting commentary to go along with this presentation. Okay, let me just hide my head over here somewhere because we're going to talk about the Tethered Mini Sumo. Hi, over here now. Okay, so this is a drawing that I've been using with my students for, as you can see, since 2003. And there's your Tethered Mini Sumo down there. And this is a dual H-bridge motor control up here made out of basically scrap parts and some nuts and bolts and screws. And so in this presentation, we're going to take a look at how we control those motors with it and why we'd call it a double H bridge. Okay, and also why we'd call it an H bridge in the first place. So to get started on that, let's just take a look at what the single H bridge is. And single H bridge is for just controlling one motor. Now, obviously, with your Mini Sumo, so that you can turn, you're going to want to be able to control two motors. And rather than just making the motor go on and off, which would be a unidirectional controller and basically just a switch, we want to be able to make the motor go forwards or backwards. And that allows the robot to turn by moving one motor forward and one motor backwards. So we need independent control. So each motor is going to need an H bridge. And you're probably looking at that and saying, gee, Jason, why don't they call it an 8 bridge instead of the H bridge? Because that really looks like a figure 8 right in there as much as it does the H running right across in here and up and down. It's called an H bridge. Um, and it's actually a really neat interface between electronics and the machine. It's where the electrons meet the motor. And really, it consists of 4 switches that can be open and closed. Now, this is 4 single pole, single throw switches. So 4 very simple switches. We're going to make some slightly more complex switches, and we'll throw out a whole bunch of acronyms like SPDT and SPST and DPDT as we go along. And at some point on one of these slides, I go through and I actually explain what they all are and what they all mean. I know you've heard me say them already, but a little review is pretty good. So here's our motor, and what we know about our electric motor, because these are brushed DC electric motors, very simple motors, very affordable, and very common, is that if you hook them up to electricity in one direction, then they spin in one direction. And if you hook them up to electricity in the other direction, then they spin in the other direction, thus giving us forwards and reverse. So over on this side, we've got our battery pack, and positive power comes right up here. And if I close S1, then electricity can flow down here. Can't go through S3 because S3 is open. Okay, and if I close S1, it comes in here and it makes this side of the motor positive. And of course, electricity needs to get out from the motor, so it'll come out the side through S4 and come back to the battery pack, and that will complete a loop, and that will spin our motor. In this diagram, I've said clockwise. Now, one way to get the whole motor to spin backwards would be to unplug the battery pack and just swap the cables over and plug it in backwards. But that would probably affect your performance on the Mini Sumo playing field if you were doing that every time you wanted to move around. So we've got a way of doing that effectively and quickly and efficiently using switches. And what we do is we let go, very important, we let go of S1 and S4, and we close S3 and S2. Well, now this positive electricity comes right up here, comes down in here, and now the positive that used to be going to the positive side of the motor is not really a positive and negative side of the motor. I've just got a nice diagram that looks that way. Comes in right here. So this side of the motor is positive now, and the electricity can get out through S2 and come back this way, spinning the motor counterclockwise in the opposite direction. So that's the fundamentals of it. You can make it up with 4 really simple switches. Now, if you're doing it with 4 really simple switches, you have to remember which ones to press. And again, you don't want to be doing that in the heat of competition. So we're going to take a look at ways that you can make it so that it works really quickly and smoothly for you. I jumped through a couple of slides there. All right, now there are a couple of unusual H-bridge configurations that we would like to avoid. And the worst one is when S1 and S2 are both pressed, or if S3 and S4 are both pressed. Because what happens then is the electricity doesn't have to go through the motor, it just goes through the switches, and they're very, very low resistance, or very low impedance, to use the AC term, switches. Basically, they're a short circuit. And so if you have this situation right here, and you press both those switches down at the same time, you'll know about it because you'll probably start to smell your batteries, and then you'll reach down and you'll feel them. And this is if you're lucky, because if you're lucky, you'll notice before your battery pack melts. This is one reason why I haven't started using lithium batteries with my high school students just yet. Nickel metal hydride batteries, alkaline batteries, I suppose if you pack them in tight enough, you could eventually get them to burst into flame. But lithium batteries present a real risk of going up in flame when they're short-circuited. They don't like that at all. So I don't use them because this happens at least a couple times every year. And so I'm telling you about it now so that you pay attention to it and you're aware of it. And if your batteries start to get warm, that's a sign that you're doing something wrong. And if they start to smell, that's a sign that they're getting warm. And if everything stops working because you've melted your battery pack, that's a sign that your batteries got too warm. And yes, that does happen kind of regularly. And that's one of the reasons why I don't buy batteries for anybody. There's also an unusual configuration right here where S1 and S3 can be closed. And that's really not a problem, because if you look at that, what you've got is, sure, that's kind of a closed loop right in there, but you're applying 5 volts to this side of the motor, or 6 volts, or whatever your battery pack is giving, maybe 9 volts or 12 volts, and you're applying the same to that side. So the two sides are kind of pushing against each other, and there's no current flow in either direction because the voltage is the same on each side of the motor. Now, the final configuration is kind of cool, and actually it would sort of work in this condition too, but if you're trying to spin the motor and you've got S2 and S4 closed, or S1 and S3 closed as well, what's going to happen is that the motor, if you're spinning it from outside, the motor is going to be acting as a generator. And when the motor generates current, if you close these switches, it feeds that current back into the motor, but in the opposite direction that it's being generated. And what that does is that the electricity that the motor is generating works against the motor itself, causing it to break or come to a stop. So this is where electronic braking comes in. And if we were really fancy and hooked the motor back up in the opposite direction to our battery, which would require more switch gear in there, what we'd actually have is regenerative braking, which is one of the reasons why electric cars are so efficient. When electric cars coast to a stop, you take your foot off the gas, okay, or they still call it put your foot in the gas when it's an electric car. You take your foot off the pedal, and as the car rolls to a stop, the kinetic energy stored in your vehicle going forward keeps turning the axle shaft, thankfully, which turns the motor, which generates electricity, and thanks to the switchgear in your motor, runs that electricity back into your battery, so that after you've coasted down a hill or coasted to a stop, you can reuse the portion of the energy that you were able to capture to get going again. If you don't have all that fancy switch gear in there, it just serves as a brake. And while it won't stop your motor instantly, it will sure take off some of the high RPM on there. And you've probably felt that when you've let go of the trigger on an electric drill. Cordless electric drills, you know how when you let go of them, they'll kick to a stop. What you're seeing is this being shorted right in here, and the energy of the spinning chuck is fighting against itself inside the motor. Very cool stuff. Okay, now I'm going to actually break this presentation down into two parts. So this will be a fairly short video relative to some of my previous videos. Anything under an hour is considered relatively short, but I'll split this one into two parts because right now we're talking about how to build your own switched mechanical, I'll even say, dual H bridge. A little later on, I've got another part of this presentation that I'll record a lecture on separately about how to hook it up for your BoomBot where you're using semiconductors to do the role of the switches. So in here, I want to take some time to talk about what I call the Cheapo Tethered Sumo Dual H Bridge. Okay, and it came about because when I was teaching this class at David Thompson, we had the sheet metal and we had the aluminum for the wheels, and it was relatively inexpensive to build these tethered mini sumos. We'd use Tamiya gearboxes that we could get for $5 or $6, but that was starting to approach the limit of my budget per student for this project. And so I couldn't go out and just buy switches for them. So we had to come up with a way to make them. And I think this is about the cheapest way to make switches, that will work for this application. And the trick is when you get packages like this, and you'll get lumber delivered to your shop, or if you've ordered your sheet metal for the year and it comes in on a pallet, it's probably strapped down. And if you're lucky, it's coming down strapped with metal strapping, okay, or metal banding, packing straps, whatever you want to call them. If you're not getting that delivered into your school, next time you're at the hardware store, just go for a walk through their lumber shop area and take a look, because a lot of the times when they get pallets of 2x4s and that delivered, they're all wrapped up in steel strapping, and they've probably got a bucket of this stuff sitting around in the back, and it's going to cost them money or whatever to have it taken away and recycled. And what I'll usually do is I'll get rolls of this waste material, chop it up into lengths, and throw it on the shelf in the back of the shop until I need it, because you can never rely on getting an order of lumber delivered exactly at the moment that you need metal strapping for your project. So just keep stockpiling it in the back, and when you retire, somebody's going to walk into your shop and say, "What the heck was all this garbage stuff back here for?" Anyway, you want about a foot of material per student. Of course, if you get 30 centimeters of student per student, that's much better because that's metric units. And I don't know exactly what the steel is, but this is what it looks like. It works really nice in these applications. Based on what I was able to find for the material properties, I think it's probably a medium carbon steel that's been cold rolled to get it nice and flat, because you'll notice that when you bend it, you can give it a bend just twisting it by hand, but it springs back, and it's that springiness that we want, because when you push down on that button, that's great, you want it to push down, but when you release it, you want it to spring back. And I've tried other materials that you're likely to have in the shop, but because they haven't been cold worked, their yield strength is still a little bit low, and they don't have that springiness to them. I've had a little bit of luck with thin tin plate. That works okay sometimes, but the aluminums, the brasses, maybe some shim stock would work, but then you're getting kind of expensive. The whole point is we're making this out of garbage. Anyway, I've used this quite a bit and it works really well. And in fact, we do a project called the Robot Mask Project, which is having one student wear a mask that completely obscures their view of anything except for a number of LEDs in front of their face, and their partner has a controller with these little switches right down in the bottom corner right here, and they can use that to turn the LEDs on and off. And the partner with the controller has to use their partner, who is the human cyborg, and guide them to complete a mission wandering around the school. And we've had a lot of fun with that. So anyway, you'll notice a couple things on here. Of course, this is the strapping is painted to protect against corrosion. The painting also protects really well against low voltage signals like we're going to be running through it. So I've taken some time to sand this down right here, and of course sand it down on the underside here where it contacts into the other screw. Um, so anyway, so you start out by making a momentary. Okay, momentary means that when you push it down, it's on, but when you release it, it turns off. SPDT, single pole, double throw switch. So one input, two outputs. And so you take a piece right here that's, yeah, I don't know, 8 centimeters or so long. You want to think about how big your hand is and think about ergonomic fit. So, you're going to be holding the controller in your hand like this. You don't want them to be too long, because if they're too long, then you've got to move your thumb back and forth and you can't control your robot quite as quickly. But you don't want them to be too short, because if they're too short, then you have to push really hard in order to get the movement to go down and touch the screws, because you got to move them through a big angle right down here. So this is just some guidelines for getting started. I'll show you some pictures of some fancy ones that students have built later on. And use whatever screw you want. I'd suggest a number 6 or a number 8, but whatever you could have on the shelf or have buckets of. And like I say, make sure you sand off the paint so that you've got good electrical contact top and bottom. And then bend a little bend into your strapping here. When I modeled this, I did it to exactly 15 degrees, but really you bend it so that when they're in the rest position, they're not touching right here. Okay, but when you press down on them without too much stress or pain on your fingers, you're going to be able to get that to touch down and make good electrical contact between the sanded bottom side and that connection right there. So what's going to happen is that when you put an electrical power into right here, if you push down on this side, it connects it and comes out right here. And if you put it at, well, of course it's coming on this side, and you press down on this side, it comes out right here. Nothing too fancy going on right there. And that's one of the reasons I like it. When you do this with the grade 9 and 10 students, they can actually see it happening and see what a switch does. And as you'll see in just a moment, this actually looks like the schematic symbol for a single pole double throw switch. Now, in order to make an H bridge, you need a momentary double pole double throw switch. So what you're going to have is you're going to have double pole, 2 inputs. So that's what the double pole means. And then the double throw means you can throw those 2 switches that way, or you can throw the 2 switches that way, and it happens at the same time. So really, you just start out and you go ahead and drill out, what's that going to be, 6, 12, 14 holes into a piece of MDF, or 1/4 inch stop. What you can use plastic, anything non-conductive. Obviously, you can't do this out of sheet metal, because that would kind of defeat the point, having electrical shorting out back and forth between here. Leave enough room so that if this wiggles off to the side back and forth, sometimes students don't get everything perfectly parallel, and if you have contact between here and here, you may have a short circuit. Okay, and you can set up one double pole double throw switch to create one H bridge. So this switch on this side will control one motor. This switch on this side will control the other motor. And make sure you put, a couple holes in here for strain relief. You thread the wire in and through there. So I'd come up from below down here, up over the top, and then down on the bottom on this side. And what that means is that when you're getting excited in a match and you pull up on the controller or something like that, the stress of lifting your robot off the playing field, which is totally cheating and you get disqualified for it. When that happens, the stress in the wire gets picked up by the board itself and not the electrical connections on the back. So anytime you're building a wired connection in electronics, make sure you include some strain relief. But I know you've heard me say that a few times before. Strangely, people still don't listen sometimes. Anyway, there you go. This can work out really well. And the washers are great for hooking things up, but if you're being really cheap, you can get away without them. So let me pop right down over here now. I'm getting better at remembering to hit the transition button over on OBS Studio when I'm recording this. So, okay, this is the what I call the fancy pants H Bridge switch, and basically anytime you go and buy the switch for the students, it's the fancy pants one. And here in 2021, as we're hopefully at the tail end of the great pandemic of COVID-19, in order to speed up our process in the shop, I've actually gone out and purchased everybody two double pole, double throw, momentary on, off, on switches. Now, that's a lot of words used to describe a switch, but it's important that you pay attention to all those words because if you don't get a momentary switch, it won't return to the off position when you let go. And if it's not on, off, on, then the other thing that's going to happen here is that you'll always have the motor spinning in one direction or the other. You need that on, off, on so that you've got that dead zone in the middle where this terminal right here is not connected to this one or to that one. Because keep in mind, think about how that El Cheapo switch was working. When you push down here, this contact right here is going to connect to right here. When you let go, this contact should not connect to right there. When you push down here, this one should connect right here. And when you let go, it should not connect to right there. And of course, that same thing's happening on the other side. So you've got two physically distinct switches in here, both following the same process depending on how you press the switch. So be really careful on how you specify your switches. There are thousands of different types of switches out there. They all kind of fit into a couple of standard categories, but you have to use the right terms to describe them, because if you got the non-momentary switch, it would still work, but in order to make your robot stop, you'd have to throw the switch into the middle position to get it to stop. And I've tried that, and it's surprising how often you throw past that line and go into reverse. Anyway, my current cheapest option right now is $2.04 Canadian each in quantities of 50 for the SW311-ND DigiKey part. And that works out really nice because if you buy $100 worth of stuff, DigiKey gives you free shipping, and they have amazing shipping. They could teach Amazon a lesson. Yes, even Amazon Prime. Sorry, Jeff Bezos. So anyways, you'll notice that it's got 6 terminals down here. Wires up just like the El Cheapo H Bridge that I'm going to talk about in a moment. And you can use either a crimped connector that you slide onto that right there, a tab connector, or soldering to connect your wires right into here. I've included some dimensional measurements right here. So if you're going to laser cut an MDF board, I would recommend using 1/4-inch MDF. You could probably even get away with using some plastic for this if you wanted, but we've got lots of MDF and it's cheap. So if you wanted to laser cut something, cut it into a nice ergonomic shape, figure out where your thumbs are going to be so that you can hold it so that your hand works with it. And you'll notice right on here, I gave you the portion of the data sheet that tells you how big the panel piercing should be. So when you're drawing it up in AutoCAD, make sure that your switch has a spacing of 19.2 millimeters by 12.9 millimeters. You might want to add 1/10 of a millimeter on each side just to make it an easier fit, but this is what they recommend. And then you'll be able to pop it into the board. It should go down flush so that all you see is this little bezel up here at the top, and these little springy things at the back should be holding it in place for you, and then you can go ahead and wire it up. Remember to put 2 little holes for your strain relief into the board. If you're doing it on the laser, why not do 2 little slots? Okay, so now we want to talk about wiring it up and how it wires together, and I've tweaked that original diagram just a little bit so that instead of this switch going this way, it goes that way, but it's the same thing. And now you can see that little pattern. There's that bent piece of metal from our El Cheapo controller. And we've got 1 terminal at the middle, 1 terminal on this side. So 1 screw here, the middle screw punched through the middle right there, and another screw on the other side. And that is 1 single pole, single throw switch. Down here, we've got the other side of our double pole, double throw switch. Okay, so two single pole, single throws makes one double pole, sorry, getting ahead of myself. Calm down. Too much coffee. I say as I have another sip. So right here, just right here, S1 itself is a single, oh, go back, single pole, single throw switch. Now, if I put two of those together, there's that nice little shape that we bent out of the metal strapping, okay? They form a single pole, meaning there's one input, double throw switch. So that one input can either be directed to that output or to that output. So two ways that you can throw the switch. Now, if I take two of the single pole double throw switches, so there's one and there's two, now I have a double pole, two inputs, okay? The poles refers to how many inputs you have. Double throw, the throws refers to the output positions that you have, switch. So right here, I have a DPDT switch hooked up to one brushed DC electric motor and one power supply over here. In our case, a 4xAA battery pack. Okay, now if you were to just hook it up directly like that, you'd press down and S1 would close and S3 would close, and you'd be in that situation where nothing would happen because you'd have positive voltage on both sides of the motor. And if you were to push down, you'd get S2 and S4 to close, and you'd have nothing happen because both sides would be connected to ground. You'd have your braking situation happening there. So we do need to do one little wiring trick to make this all work, and we come back to this original drawing that I've been using for many, many years. And let me just come hide up in the top corner over here. There we go. So this is the wiring diagram, again, that I've been using. Gosh, it's almost 20 years now, soon will be. And as you can see, I didn't have Fusion 360 to render my drawings. I had to go through, sketch them all out in pencil, and then go over them in Sharpie so that they were nice and dark, and then I could put them on the scanner and get them scanned in with some degree of image quality on here. It actually was a fairly pleasant experience and probably quicker than doing stuff up in Fusion 360. Now, the key thing we want to take a look at, so you can see the top right here, and we've got our left motor controllers and our right motor controllers. We want the motor to go forward when we press up and reverse when we press down. We've got our strain relief right in there, and we've got about, I don't know, 4 feet, 1 meter of cable coming back to the robot, and 6 conductor cable because our batteries are on the robot. Now, if we flip it over and look at the back right here, okay, we've got 6 conductors coming in right here. And where do those conductors go? Let me see if I can get a pen on here, and let's follow the power as it comes in. So here is our power coming in, and that comes to this terminal, and we jump it over to this terminal, okay? And then we've got ground, and our ground is going to come in right here to that terminal. And pardon my mouse-based drawing skills, over that terminal. So now each of our 2 switches has power and ground going to the center pins of it. So if I push up on this side, now I'll get ground connected to right there. And if I push up on this side, I'll get positive connected to right there. Okay, now, unless we've got some more connections in there, that's not going to do much. Okay, you can see I've labeled this motor 1B. On this side, that jumps over to here, and that goes back down in there. So I get positive going to motor 1B, and our negative jumps down here, comes out here, and I get negative going to the 1A input. In other words, I've got the motor spinning in one direction. Okay, since I've pushed up, let's hope that that's forward. If it's not forward, then all I need to do is change motor 1A and motor 1B right here. Just swap those two connections from the robot back and forth, and I will be going forward. Or you could swap the positive and negative right in here, and you'd be going forward. Now, if I push down, let me see, how do I clear all that out of there? Well, clearing some lines I didn't want to clear. Okay, this side's still positive. If I push down, then my positive now comes down this way, and you can see that now it's connected to motor 1A. Now, it doesn't matter that it comes back up here because that's not where it's connected to the motor. This is where it's connected to the motor, and it comes down and it goes off to the motor. And by pressing down now, my ground comes down here. Now my ground is connected to motor 1B, and that's the exact opposite of what we had hooked up before. So by pressing up or down, we can swap those lines back and forth, and rather than unplugging our battery and plugging the battery in backwards, we just use a double pole, double throw switch to do it. And whether you've got a store-bought switch that has 6 terminals coming out like this, or whether you've got a homemade one that you've thrown together in the shop for 50 cents or less, then you're able to do that. And 2 of those switches put together gives you a dual H bridge motor controller. So one side controls one set and one controls the other. Now, if you run into problems with this, then it's really easy to fix, particularly if you haven't soldered things in place. Because if all you've done is stripped the ends of your wire and made a little loop with the wire and sandwiched it between those 2 washers. And I do recommend you using the washers. You don't have to. You can wrap them tight around the peg and squash them down. But the 2 washers makes it nice because then you can got nice flat surfaces. You squeeze your stripped wire in between them, and lo and behold, you're good to go. If it's not working, as I said, one motor's spinning in the wrong direction, well, just swap your connections here or swap your connections there. Either one of those makes that motor spin backwards. If your left set of switches is hooked up to your right motor, so in other words, you're driving and you hit this switch and that motor moves, and you hit this switch and that motor moves, so everything's backwards to what you want, then what you can do is just disconnect the motors from right here and from right here, and just swap those wires back so that each motor is connected to the correct controller. Now, if you start to smell smoke, that's also another problem, and that probably means that you've got a short circuit in there somewhere. So don't panic. Take your batteries out, figure out where that smoke's coming from. You may have to go buy some new batteries. That's why I don't buy batteries for students. It's amazing how much more careful students are about checking to make sure that they don't have short circuits when they're working with their own batteries. Of course, in a high school setting, not every kid's going to be able to bring a set of 4 AA's in with them. So, take into account that we are an equal opportunity education system. Okay, so if your motor's not working, maybe you got an open circuit, at least you're not sending things up in smoke. So use your multimeter to test all your connections. Make sure that you sanded down the paint off of your strapping. That's one that people sometimes forget. And maybe your batteries are just dead if you just had a short circuit a while back. So anyways, take a look through that. It's a fairly simple thing to set up, and you can take that simple concept, and once you understand what you're doing, you can start getting really fancy with it. And here's some different controller setups that students have built over the years. This is the basic setup, but in a more ergonomic setting. Here a student had their own momentary double pole, double throw toggle switches right in here. So a toggle is one where there's a lever arm that moves back and forth as opposed to a slide, which goes forwards and backwards. Most of your momentary ones will be some form of toggle. And here somebody made their own toggle switch right in here. And what you'll see that's really common between this design, where you've got little pieces of wire bent right in here, here to make the contact and springs sitting right in here to make the contact, is that the springs allow for this contact and this contact to connect at different times more easily, because if your tolerances are slightly off or things are bent slightly, you'll have one contact hit before the other. If your thumb's not right in the middle of that piece of wood on the inexpensive H bridge, um, anyway, the springs just allow for a little more tolerance on your metallic contacts. Here you can see some shorter springs and a nifty job sandwiching it between a couple pieces of acrylic. And rather than just soldering things on or wrapping wires on here, they used crimped connectors on here and ring terminals. And they did a nice job of using color-coded wire so that they could track where all their electricity is going and how it's working. So really neat stuff coming together from students over the years. Like I say, if you're doing this project with me in 2021, I bought some switches for you. You don't have to go ahead and do that. But when you're doing this with your students, it's quite possible that you'll be wanting to do a less expensive version using materials that you're likely to find around the shop and not have to add $100 worth of switches onto your budget. Um, Later on, I'm going to come back and talk about the rest of the presentation, because eventually we're going to want to use microcontrollers to control this. And in that case, we're going to be using transistors or microchips as we get to everything built into an electronic circuit board. But for now, have some fun, and I look forward to seeing your Tethered Mini Sumos rolling about the floor in short order. Okay, good luck, and I hope you're able to solve all the problems. I'll leave it on this slide right here because it's got all the wiring information you need. But just Google that. I think if you Google Tethered Mini Sumo, this is going to be your number one hit on Google Images. Have a good afternoon, or morning, or evening, or whatever it is, as I speak randomly while I try to remember where the stop recording button is.